Officially on the syllabus, today we were going to do shortest paths and finished graph algorithms. But what I'm actually going to do is backtrack a little bit, make sure everybody's on keel with depth first and breadth first search, understands the difference between amortized time and just regular average case complexity, work my way toward shortest path, maybe even get started on it today, and then we'll finish it off next time. I have 2 lectures officially on geometric algorithms, and we could spend a whole week on those too. We could spend a whole other week on graph algorithms. I mean, God knows every application in algorithms, you can go on and on and on, and then follow the branches. But you're supposed to get a nice, good, solid background in 1 month, and you can't do everything. So the geometry algorithms I won't spend as much time on as I hoped. I might end up just spending 1 lecture on that, because we're going to do this one algorithm. We're going to do convex hull. It's like the sorting of geometry algorithms. And there's some other variations of that you'll see in the problem set, but we won't do too much more. And I think we'll still be right on track to switch gears from applications next week to dynamic programming, to techniques rather than applications. And after we're done talking about algorithms by technique, then we head towards NP-complete problems. Quick review. I want to make sure everybody gets the difference between amortized time and worst case, average case. 5-minute quick review. Amortized versus worst case versus average case. Let's start with the easiest one. If I say an algorithm is worst case time complexity, say log n, it means that I can come up with an example where that algorithm will take that much time. Okay, I'm the adversary. The person who creates the example is the adversary. The person who creates the algorithm is the opponent, and you come up with your algorithm, I come up with my example. If I can make your algorithm take this much time, then that's the worst case. All right. Here's an example of worst case for quicksort. You come up with your quicksort algorithm. I can plan the data out so that your algorithm will run in n squared. I can make sure that it's ordered in such a way that it makes the wrong partition every single time and ends up being order n squared. In practice, if I analyze what will typically happen over all the possible distributions of numbers that I could throw in, and calculate all the complexities and divide it by all the different possible distributions that would come in, that's average case. And for quicksort, it would be n log n. That does not deny the fact that if you got a peculiar distribution, that you wouldn't get n squared. You still might get n squared on a bad day. But over the average of doing a lot of these, they would average out to n log n. But if you could conceivably even have a lot of bad days in a row, and it would be n squared over and over and over and over again. Okay? Everybody get it? The chance of that is low, but it can happen. There is a chance of that.
Is it the average time complexity or just the average case that determines that? Say you have one really, really bad case. Does that just get averaged in?
You mean one particular partition in the many recursive partitions in a particular quicksort?
Yeah, like one particular set of data that the algorithm is going to operate on that gives you a terrible time.
That all the partitions are bad and it gives you an n squared. That's the worst case.
Yeah, but does
yes.
that case get averaged in?
Sure.
Okay.
That's included in this order n log n comparison. There are many n squared situations, but there are so many more of the n factorial distributions that are closer to n log n or even faster that they average out to this. The vast majority are n log n, and a few of them are n squared, but it averages out to n log n. And we do that with a fancy recurrence equation that Mike Allen ran a recitation to talk about the details. All right, that's average case, worst case. And you can see why you'd want average case, because some things work really fast, even though their worst case is bad. So you calculate an average case.
Would it be correct to say that with the randomized algorithm actually changes the worst case to n log n, or just that
no, you still have the same worst case, but your chance of that worst case showing up becomes smaller. That's what you could say.
The adversary can't specifically give you a set of numbers that's going to give you the worst case.
That's right, but they could get lucky and give you a set. Right, the adversary becomes helpless, but a nice monkey working enough days in a row would still give you an n squared. All right.
Shai?
Yes.
After he finishes typing checks
If the
Right.
order varies on n, like even, odd, prime, composite, something like that, would you average over various n's? Or is this all assuming a stable n?
Yeah, ask the question again, 'cause I'm not sure I understood it. Yeah.
The average cases for n are for the different permutations of data.
Right.
But what if, as n varies from even to odd or prime to composite, the order changes? Would you average over n's?
You mean if for particular lengths
Yes.
of the sets of data, like for, say, lengths that are prime length,
Yes.
and you want to just check what's the average there or what's the worst
No,
case
whether-
there?
well, if it's much, much better if it's a prime number, then would you look at the distribution of primes and say now the average is less than it would otherwise be?
You could, but I would be doubtful that you would notice a difference in either of these results if you restricted the size of your data to particular kinds of numbers.
Yeah.
I don't think it would matter, but you could certainly do that. And it might matter in other algorithms. Other questions? All right, last case. This is the case that I want to make sure we distinguish from these two. Amortized analysis. I've been using quicksort as an example because quicksort's a good example of where amortized analysis has no effect at all. And maybe to understand where it has the most effect is to understand a case that it has no effect. Amortized analysis works well when you have an algorithm where when the algorithm's finished, the fact that it's finished affects the running time of when you run it again. Let's say I ran quicksort on this data, and it did something to the data besides sorting it. Did something so that the next random set of data I got actually made quicksort run faster. I mean, it doesn't. Quicksort sorts data, and it doesn't affect the next set of data. But if it had some mystical effect on the next set of data that made the next set run faster, then amortized analysis would make some sense. Amortized analysis is for algorithms that when you run them over and over and over and over again, the subsequent runnings are better off because the early runnings took place. Subsequent continuous running of the algorithm will affect upcoming computations. So when does that happen? The most common case where that happens is a situation where you're talking about an algorithm that runs on a data structure, and that algorithm is called over and over and over again in a data structure, like find for the union find, like insert for a heap. Anything like that where you're going to do it over and over again. It's possible that if you massage the data structure while you're doing the algorithm once, then the next time you do it, the algorithm runs faster. That's basically what amortized analysis is. So when we came up with that path compression for find, we had union find data structure. We had a find algorithm. The find algorithm, worst case, is definitely order log n, even with path compression. You can have a bad time. You can have a bad day where it actually takes log n to do one of the finds. But having a bad day with a find makes the next 20 have good days. It's just like a savings account. It's just like the idea of amortizing. Having a bad one affects subsequent ones and lets them have easier ones. So it is impossible, not on the average, but it is impossible ever to have lots and lots of finds, each of which take log n. Specifically, if I have p finds in a row that I've called, they will never be p log n. Even though one might be p log n, the collection of them will never multiply up and be the worst case every single time. This is a stronger result than average case. If I said this for quicksort, I'd say, well, quicksort's worst case is n squared. But if you do 10 quicksorts, the worst you're going to get is 10 n log n. That's not true. You do 10 quicksorts, and the worst you're going to get is 10 n squared. Everybody get that difference? But here, if I do p finds, the worst I'm going to get is p log star n, a function which is much smaller than log n. That's what amortized analysis is about. It's not saying that you will always, it's saying better than you'll always get an average case. It's saying you will avoid the worst case completely as long as you do this a lot. Yeah?
Are you assuming you're finding different things each time as opposed to finding the thing that's the furthest away and doing that 10 times?
No,
No?
You can come up with an example where p things in a row would take p log n, even if you try.
Even if it's the same thing and it takes log n to find it, and then you just say, we'll do it again.
Because the data structure's changed.
Okay.
Because when my find goes through it, I fix it so that if you try to do that again, the next time it'll be fast.
Okay, because it's union thought.
Right. It's a little bit like hashing. It's like if you say, I want to retrieve this value, and then it takes a long time to do it, and then I take that value and I put it in a cache right up in front, like architecture. Then the next time you try to do it, you get it fast. So every time you try to make me slow down, I end up speeding it up. So the data structure is kind of adapting to your strategy. So the answer is no, you can't do it. So it's a really powerful analysis tool. Yeah?
Is there ever a case where an amortized analysis makes things worse? That is to say, the first time you do something, it's not so bad, but if you do it a lot, it gets really bad?
Why would we use them?
Well,
Just curious.
I don't know a good example, but I probably could construct it. But like Sam says, I mean, it's not going to be something anybody's looking for, but it might be something that might show up. You might think, but you see, you wouldn't be. You're always doing worst case, so it's never going to be worse than p times the worst case. So yes, I don't know a good example of that, although it's an interesting thing to think about. I'll think about it and see if I can come up with an analogy that I think comes up, because it might. Other questions? Good? Everybody get this? Review done? All right. Next thing. This is not review. This is more of an ongoing thing. We talked about depth first search last time, and I want to nail this down, make sure everybody understands it. And I want to talk about it in the context of the problem set that you're going to work on right now. So it'll help you give some hints and also put it in context of something which is a little more code-like. Before I do it, just very, very briefly, just to clarify, because we talked about this only for a second yesterday, and I hesitated, and I want to make sure that everybody knows the right meanings for these. Cross, forward, back, tree. I'm going to describe these different kind of edges that come up in a depth first search. When you go forward in a depth first search to a node that was previously unmarked, that edge becomes a tree edge. And we'll remember a parent back, and we typically remember the depth first search tree. A directed graph and an undirected graph have a depth first search tree, and they are the edges that you first flood forward on. Anytime you get to a node and you look down an edge and you head to something that was already marked or seen before, that's not a tree edge, it's one of the others. The main thing you should think of is there are tree edges and then there are other edges. In an undirected graph, that's all there are. There's tree edges and there's back edges. Either you're going forward to an unmarked place and there's tree edges, or you're going to a place that's already marked and that's back in the tree that you've seen before. There's no arrows, so everything is just back to the tree. But in a graph that has arrows, a directed graph, there are three different kinds of edges that are not tree edges. There are back edges. That means if you think of the tree as the arrows going forward from your root, then a back edge is something, if you're here in the tree, that goes back up the tree further up. That's very common, typical. A forward edge means you've done your depth first search here, you've backed up to here, you've done this, you back up to here, and it turns out that there's an edge over here, from here to here, on your way back. That's a forward edge. Any edge which is pointing to something that's marked, and that thing that's marked is further down the tree, that's a forward edge. That can happen in a directed graph. Actually, if you look at the example we did yesterday in class, that actually happened. We had a forward edge.
Can you show that again in that graph?
Yeah, I didn't draw the other edges, so you can't see it. Maybe I should draw the example we did last time, and we'll see it on there. Except I don't have that example. Thanks. Perfect.
It has a back. You said it didn't have any back edges? The one we did yesterday?
I don't know if I know it has a forward edge. Here, I'm gonna draw it out. Anthony's got good notes. 7, 5, 6, 7. Does that look like it? Does anybody else have these now?
Yeah, that's it.
Okay.
Those are, there's other edges. Those are just,
That's the tree. That's the tree edge. I'm going to dot in the other edges now. There's one here, right? There's one here. And there's one here, right? And there's one. Oh, this really is a tree edge too. Is it?
No.
No, it's not. Okay. I see. I got you. Okay. This was our depth first search tree on this graph yesterday. Thank you. That's helpful. All the dark edges are tree edges. What's this edge? A forward edge. It's moving to something that was previously marked, which happens to be down the tree.
So down the tree means more nodes from where we started?
More nodes down from the root. Right.
There's multiple ways to get to that.
There's not. A tree has a unique path between every two nodes.
Okay.
So there's only one. It's either up or down. Are there any back edges? A back edge is something that would go back up the tree. In this example, I don't think there's a back
How about
edge.
the guy from 7.5 to 5.3?
From here to here,
Yeah.
that's neither back, because this is the root.
This is 2.
Right, so it's either, back would mean straight back up the tree, forward means forward around the tree, and anything that isn't back or forward is called a cross edge, because this goes from, it's basically incomparable. It's neither back nor forward, so we'll call it a cross edge.
Why is that? Because they're an equal number of...
Because this is the dead end. If you entered the cave here, and you said, from here to here, is it back or forward in the cave? You'd say, well, neither. You got to go back, and then you got to go forward.
Equal number of nodes from the root.
No, it doesn't have anything to do with how far it is from the root. It has to do with, if you go back from here, if this heads to a node, which is on the way back from here to the root, that's a back edge.
Okay.
If it's further down from this, it's a forward edge.
If it's off a different branch from node, then it's always across.
Always across, right.
From 7.5 to 2.4 would still be a cross.
7.5 to 2.4 is a cross. 7.5 to 1.8 is a back edge.
7.5 to...
4.1 to 2.4 is a back edge.
Suppose
Right.
you have a graph that's a mixture of directed and undirected edges.
I guess any undirected graph can always be made into a directed graph because you just put two edges back and forth. So if you have any directed edges, you just make it directed. I guess that's what you do. Okay, questions about these? I'm not going to spend too long on these, but I want you to know what they are because a lot of times when people talk about depth first search algorithms, they prove theorems and they say every back edge has to have this property and therefore we do the code this way. So you should know what they're talking about. All right? Cross edges and forward edges and back edges, remember, in an undirected graph, they're all the same. They're all just back edges. All right. Questions about this? All right. That's a little bit of review. Now what I want to do is write a teeny, not real code, a little pseudocode up on the board, which will be kind of a depth first search skeleton. We'll use it to solve that problem that I mentioned really briefly at the end of last class, the connected components problem. And then I'm going to relate that connected components problem to the scoring problem in the game that you have in your problem set, because they're extremely related. The idea of a depth first search skeleton is you have this little bit of code that's about 6 lines long, and then you just flush it out in 3 different places, and depending on what you put in those 3 places, the algorithm does completely different things. For example, if you put in, print out the finishing time in the right place, it'll do topological sorting. If you put something else in a different place, it'll do connected components. You can flush it in, add extra data structures, add extra lines, and it'll do all sorts of cool stuff. All right, so here's a depth first search skeleton. There's 2 parts to it. The first part is the actual depth first search itself. Now you might have a lot of other data structures in your problem, but you always will have some data structure which marks the vertex that you're about to search. You have some array that remembers that you've now seen this, because you absolutely have to remember which ones you've seen. Otherwise you have no way to know which ones to skip or which ones are back edges later on. Now sometimes this is done with a number or a count rather than just a mark, and you increment that count each time. If we wanted to come up with these early visit numbers, 1, 2, 3, 4, the early ones, 5, 6, 7, 8, then instead of doing mark, we could have another number called early visit, and we would set that equal to whatever the current counter was up to. So you can mark it here, you can set the early number here. This is the pre-time. This is when you're just about to start the vertex. All right, what's the next thing you do? It's very easy. It's 3 lines of code. We are now going to recursively call depth first search on all the children that are not yet marked. Okay? So for all j adjacent to I, if j is unmarked, that means if mark of j equals 0, if j is unmarked, do depth first search of j. That's a depth first search skeleton. It's a bare skeleton. It says do it recursively and go depth first. Mark it. For everything that isn't marked, do a depth first search on that. Eventually this will go as far as it can, it'll backtrack, and it'll be finished. Now here's the thing. Let's run this algorithm on the following graph. A, B, C, D, E. And let's say our data structure is in alphabetical order, so A is our first thing in the array, and the adjacency list has it connected to B and C. So we mark A. I'll check vertices that have been marked. A is now marked. Our algorithm now tells us to do what? For every j adjacent to I, for every thing connected to A, namely B and C, start a depth first search. Let's assume that they're in alphabetical order. So now you're going to start a depth first search on B. Now B is marked. What's the first place you look from B?
Back to A.
Right, you're going to look back to A now, because that's alphabetical order. You're going to see that A is marked. So you're not going to get into an infinite loop here and start a new depth first search. You skip that. Okay? By the way, normally in a directed graph, when you go down an edge whose node is marked, that edge is either a cross edge, a forward edge, or a back edge. In fact, normally in undirected graphs, if you go down an edge that's been marked, it's a back edge. What happened here when we went down an edge that was marked? It was a tree edge, right? That's an edge that we just came down. It's not really a back edge. That's because in an undirected graph, a single edge gets listed twice. In a directed graph, every edge is just there on its own. But in an undirected graph, this single edge gets listed twice. Once on A's list, once on B's list. And you actually traverse it twice. And you have to be very careful not to confuse going back to A with a back edge. And I'll explain this why in a minute. But you'll see an example in your homework where you have to be careful about that. How could you check, by the way, that it wasn't a back edge? If you're creating the parent array as you go down, then you could just check if the edge you're going to is the same as the node of your parent, then say, oh, this is a tree edge. It's not a back edge. But why would you care? We'll get to later. Right. So we're not going to do a depth first search on A. We're going forward from B again. We do a depth first search on C, and we mark C. C checks A is marked. C checks B is marked. So we back up to B. B's done. We back up to A's done. Now we're finished. The depth first search tree looks like this. Notice I haven't stored the depth first search tree in here. That's extra stuff you'd add on. You'd throw in the parent array and you'd set it equal. But we have a bare skeleton. We're done. We get this depth first search tree and we're finished. But look at the rest of the graph. It's not done yet. So you can't just do a depth first search on one node in a graph and assume you'll be finished with the graph. It could be disconnected. In a directed graph, it's even worse. It could be all underlying connected, and you can start from one spot and possibly not be able to get to the rest of it, even though the underlying graph is connected. You can have sections of it that don't connect to other sections, even though the lines are all there. So this comes up even worse in a directed case. So what do? To really make a depth first search skeleton, you have to wrap your depth first search algorithm in a little loop that goes through all the nodes. And it says if I is unmarked, then do depth first search of I. Otherwise, skip it. So what this does is it starts you off at the first node at A. And it finishes B and C, and then it's all done. And now we're ready to end, and it goes on to I equals 2, which is B. But B is marked. So then it goes to I equals 3, which is C. C is marked. Then it goes to I equals 4, which is D. D is not marked. So now a new depth first search begins at D. Okay, and then you get this line coming in. E gets marked, D gets marked. You come out of your second depth first search. The loop goes to 5. That's been marked, and then you quit out. So what this does is make sure that if one of your depth first searches didn't actually span that whole graph, that your loop will catch it and start a new one at the very next unmarked space. This adds just a factor of n to the complexity. Because the worst case is that you'll get all the nodes taken care of in the first depth first search call, and then you have to go through a bunch of marked nodes just checking that they're marked. So it takes your order E algorithm depth first search and adds n to it and makes it order E plus n. And that's why we always say that depth first search is E plus n, because of this loop that you have to wrap it in. Questions about that? Yes, Chris?
You were keeping track of the counters?
Yes.
Visited on and finished with counters and whatever.
Yes.
Would you start over with a disconnected graph section somehow, or is there some way to distinguish in your numbers that that's separate?
You could certainly start it from scratch. We'll talk about that right now. Let's think about this connected component algorithm, and then I'll try to answer your question while we do it. Say we wanted to simply print out all the nodes that were in component 1 and then all the nodes that were in component 2. How can we use this skeleton to do that?
A global component variable that is incremented each time we start.
So let's keep track of the components. We'll start the components at 1. So out here we'll have components equal 1. Okay? And now we go through here and we start our depth first search. This is going to go through a whole bunch of nodes and finish with a component. And when it comes out, right here, before we go on back to the next one, we will print out something like print out component number component.
A component is just all the nodes you can get to with one.
Right, right. We print out component number 1 here, but where are the nodes? We didn't do anything. We didn't store them. We didn't touch a darn thing. We can go back to the marked array now and look at the ones and get them, but then later on, how are we going to know which ones are marked? We should have stored them along the way. Where do you do that? Look at this skeleton. Where in this skeleton do you want to remember the nodes that you saw? For all j adjacent to I, right? Is that okay? Do you miss I then?
Stick it at the end.
Stick it at the end? Can you stick it at the beginning? Where are the places you can add stuff? There's the beginning. There's in this loop. There's inside this if statement. If do this, else do something else. And then there's at the end of this loop. There's one place. Inside the if statement is 2 places. After the whole loop is 3 places. 3 places.
Right after you mark it would be the safest place.
Right after you mark it is fine. When you're all done is also fine. Any place that you're guaranteed to remember that you saw this node. But I agree with Tony that the natural place is right at the beginning. You're depth first searching on this variable, so it's a node that's going to be in your component. So I'll say, this is my addition. I'm flushing out the skeleton to do connected components. Add I to a stack.
Wait, is that going to happen multiple times for nodes that are already marked?
No.
Them again? Is that
No, because we never depth first search something more than
don't
once.
even give it.
We don't go there. So anytime you see a node I and you mark it, you also add it to a stack. That's fine. So now I'm keeping track of my vertices. So right here, after I say print out component number 1, I also empty out the stack. Remember the nodes you saw? Output them. Empty the stack. Now when you come back, it goes to number 2, number 3. They've already been marked. It starts number 4. The stack is empty now. It adds new things to the stack, namely D and E. And when it finally comes back out here, it empties those out. So you get component 1 is ABC, component 2 is DE, and that's all you get.
The increment component there at the end.
Right. So before you come back, we need to take component and do plus plus. Otherwise, it'll keep saying component number 1 is this, component number 1 is this other one. Right, you're right. Got to be careful. Okay. This is a very, very, very basic way of flushing out a depth first search skeleton. You can do a lot fancier stuff in flushing out a depth first search skeleton, but I want you to realize that depth first search doesn't have to be rigid. It doesn't have to look the same all the time. It looks like this in the skeleton, but you put on the meat and make it do different things. But don't reinvent the wheel every time. Use this skeleton. Get used to this being your structure and putting the meat on this, rather than every new problem being something from scratch and redesigning it from scratch. Okay, questions about this? Let's go back to this issue of the tree edge and the back edge and talk about one of the problems in your assignment. One of the problems in your assignment is to decide if a graph has a cycle, an undirected graph has a cycle, and identify what the cycle is. Let's discuss it for 5 minutes. How do you know you get a cycle in a graph using depth first search? You're moving down your tree. You're happy. You get one of these edges. Well, this is a directed graph, so the issue of a cycle here might be a little trickier, right? How do you know you get a cycle in a directed graph? What kind of edge do you have to come up to? A forward edge doesn't tell you there's a cycle, right?
It's a vertex that you've seen before, but you're not done with.
A back edge. A cross edge doesn't give you a cycle. A forward edge doesn't give you a cycle. But a back edge gives you a cycle. Specifically, it means you have gone forward on a tree, and now you're going back to a place you've already seen before. A back edge is the definition of a cycle. Now, how would you get the actual cycle? All you'd have to do is follow the pointer array, if you kept track of that, back from the node that you're on. So that's just a little loop running back through the pointer array. Well, we didn't keep track of a pointer array. Where should the parent pointer array be? Where do you set that?
Same time we add to the stack, probably.
Right here, when you're going forward into depth first search I, how do you know what the parent is? I think you do the parent array
You would want to do it just before you call depth first search on a J.
right over here. If you decide that you're going forward from I to J, that means that the parent of J is I. So right here, in the if statement, inside the if statement, in the then part, you can also do things in the else part, but now we're doing things in the then part, P of I equals, P of J equals I. Ah, jeez, this is looking ugly. The ideas are clear, but my chalk work today is crap. P of J equals I. Change the parent of J that you're moving to I where you came from. That will keep track of a parent array. Then later on, if you ever get a back edge, you'll be able to traverse through the parent array and print out the nodes. Yeah, Tzvi.
Why is that in the if?
Because you only want to do it if you're moving forward to J, if J is not marked.
Okay.
So if J is not marked, you're going to set the parent and then do a depth first search. I guess you could first do the depth first search and then set P of J to I too. It doesn't matter which order here, but it's got to be in the then section of the if statement. Because you don't want to have the parent of J be I unless it's a tree edge. And this is tree edges here. Okay? So where are back edges?
Wait, couldn't
Yes?
if there's a cycle that goes through the beginning, the root,
The root, yeah.
couldn't the cross edge create a cycle connecting to another branch from the root?
A cross edge, but it has to be connected to a back edge.
Somewhere there needs to be a back edge.
Somewhere there would need to be a back edge.
7 to 5.
Ah, yeah. Oh, I just thought of a movie.
Eventually you get, it goes right through where you started. And if you're part way out and you connect to something that's on a different branch from the beginning node, you say,
Watch what would happen. If there were a big circle, I go tree edge, tree edge, tree edge, tree edge, tree edge, back edge.
Back edge, back edge.
No, assuming there's just a cycle this way. Then I go forward, 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 all tree edges, and that would be a back edge.
Assuming
the
you
next
hadn't
line
done
is
this
back
discovery.
edge as well. Forward, forward, cross, back, back.
well, the way we were talking, there
Yeah.
wouldn't be a back edge. Okay, but that one that connects right back to the node, that's the back edge. Okay.
Right. But directed graphs are a little trickier, but undirected graphs are easier. Okay? If you ever get a back edge in an undirected graph, it means a cycle. The thing is, if I'm going from A to B and then I go back from B to A is already marked, and you're going to think that's a back edge. Because how do you check for a back edge? It's things that are already marked. Where is that in my code? Where are things that are already marked? If J is adjacent, for all J adjacent to I, if J is unmarked, do this. I didn't put an else in, but there's an else. Else means it is marked. That's a back edge. Right. Wait a second. Right. That's a back edge. This is where you put things in if you want to do back edges. If you're writing a program that checks for cycles, that's where you check for the cycle. That's where you say, I got a cycle, here it is. And you traverse through the parent arrays. Now that would work okay, except for one little itty-bitty thing that you might actually, in an undirected graph, have gone right back along the tree edge that you just came down. And you're going to think it's a back edge because it would end up in this else section, but it's not really a back edge. So when I say back edge here, I mean back edge unless it happens to be the tree edge you just came down. So in here, you have to put another little if statement in that says, and make sure that J is not the parent of I. Make sure that you just didn't go back to the place you came from. Okay? Because we've already set I to be the parent of J. Make sure that it doesn't work the other way. Make sure that you're not going back the other way. Make sense? Think about that on your own if it doesn't make sense. You need to distinguish between going back on the same tree edge and whether it's really a back edge. So be a little bit careful in this else section. All right. That's another example of flushing out the skeleton. Connected components. Let me shift over to another problem on your problem set. There's a problem that says, look, you have a graph, and it represents the scoring in a game.
So Shai, real quickly,
Yeah.
back edge is a procedure that will return Boolean, or?
It's not a procedure. It's just a place where you can put stuff in about back edges. If you ever get there, it means you've seen a back edge. And as far as getting the cycle goes, it means when you get to this spot, you're going to run a teeny little loop that runs through the pointers back, prints out the nodes as it goes until it gets to nil, and then says, I found a cycle, here it is, break. Okay? Unless going back actually gets to the parent of J, in which case you wouldn't do that. Does that make sense, Anthony? Did I answer the question? Yeah. Okay. Here's the problem in your homework. You basically got a graph like this, and in the graph, the nodes are labeled black, white, or empty. So I'll write this out. Let's say these are white, white. These are empty. This is empty. This is black, empty, 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 black, and nope, I want to make this white. White and empty. All right. The idea of this game is you're supposed to figure out what the score is at the end. Let me make these more clear. I didn't. E, W, W, E. Oh, jeez, I'm really sorry. I don't know. Some days I just lose it with the chalk. All right. E, W's, and B's. Most of these are E's. E means there's nothing on that spot. W means there's a white thing on that spot. B means there's a black thing on that spot. The score is, add up all the whites. That counts for white. So there's 1, 2, 3, 4, 5 whites. Add up all the blacks. There's 1 black. And now, for the empties, you have to decide black or white for each one. Okay? And some of them, what?
Go scoring algorithm?
It can be used for Go, but it doesn't have to be. It can be used for any graph, and I want you to write it for any graph. An empty one either counts for black, white, or for neither. Let's decide. Let's look at this empty one. If the only paths out of the empties hit whites or other empties, white, 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 empty, 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 white, all these empties are bounded by whites. They're surrounded by whites. You can't get out of that area without hitting a white. Then that empty section is white. So these 4 count as whites. What about this one? counts as white because it's bounded by this white. This one counts as white. This one counts as black. This one counts as black. This one counts as white. This one counts as white. And this one counts as white.
Wait, the empty in the middle on the bottom has an empty to the left of it, but it's not connected.
It's not connected.
Oh, right, it's not connected.
Stop thinking about Go. It's not a grid. It's just a graph.
Which one counted as black?
I don't think any counted as black, right? Oh, these two. These two. Sorry.
But no one counted as empty either.
Right. So let's change it just a little bit. Let's put an empty here, and let's put a white here. Now, what about these three empties? They don't count for anybody. They're gray. All right.
Why is that?
Because if you move from them, you get both black and white, depending on what direction you go. They're not surrounded by either of a single color. This problem is just a disguised variation of this problem, of the connected component problem. And that's why I'm giving it to you. I want you to build on this structure. I want you to leverage the algorithm that you know. I don't want you to go and just think of this as a Java thing where it's Same game, you never saw anything like it before, and you're just going to do it from scratch. Don't come up with some ad hoc way to do it. Try to build it on what we know. Now let me convince you that it really is just a variation of this connected component problem. Okay, you're going to have to do some work. It's not just exactly the same, but it's very similar. Here's a graph. We're going to do depth first search on this graph. Let's say we start on this W. In this graph, if you're doing depth first search and you see something that's marked W or black, then you stop. And you say, I know everything I need to know about this node. It counts W or it counts black. You're trying to decide whether a node counts W or black, white or black. So this one you just return. That's easy. You never go forward. Now you get an empty. So you got to do a depth first search from here. And you're going to search and search and search. If you get more empties, you're going to keep searching. If you get a white, what do? You stop. If you get a black, what do? You stop. The whites and the blacks act as nils, act as edges, act as separations of your components. Here's one component of this graph. Everybody see that? This is essentially disconnected from the rest of the graph. Here's another component. These are areas of the graph. If you think of just the E's, then these four E's are disconnected from this one, and this one's disconnected from that one, and this is disconnected from this, and these three are disconnected from the rest. What you're really doing here is find me the connected E's in this graph. Okay? Not find the connected component, but find the connected E's. Once you find the connected E's, the issue is, what color are they? Well, here's what you do. How do you decide what color they are? This is so nice to fill right in here. Let's think about it. You're depth first searching on this E, which means you're going to recursively depth first search on all its children. When you're all done depth first searching on this E, the depth first search is going to return a value. It'll return, I saw only black on my search, I saw only white on my search, or I saw black and white on my search.
Or I saw neither.
Well, it's got to see something sooner or later. When it finishes and comes back, the only way it can come back is it's got to see.
There may be no black.
I guess there could be nothing on the graph. You're right. You're right. You're right. My assumption is that there's at least one black and white. But you're right. It could conceivably be empty and it could return neither. But let's assume there's a black and white. It's a good point. If there's a black and white on the board, when you come all the way back from this depth first search, it returns black completely, white completely, or I've seen both. How do you do that? How do you make that return happen? Well, the depth first search that it calls had to have returned black or white or both. If all the children of this one return black, then this one returns black. If all the children of this one return white, then that one returns white. And if some of its children return black and some of its children return white, it returns gray. Where do you put that? You see this loop here for all j adjacent to I, if j is unmarked, depth first search j? This is going to return a value. When it returns, you look at the value it returns. You're going to have two little Boolean variables, one that says I saw black, one that says I saw white. If this returns a black, you set that to true. If this returns a white, you set that to true. When you're all done with this loop, you look at those variables. If the black one's true, you return black. If the white one's true, you return, only the black one's true, you return black. If only the white one's true, you return white. If they're both true, you return gray. So mark the Boolean variables in this loop, and when the loop's all done, in this section, decide the color. This section decides the color based on the Boolean variables that were processed in here. Process child's color. Again, I'm being a little bit vague because this is a problem and I want you to work on it. But I'm not being so vague that it should seem dense. You should realize that you can just take this structure, put in a little code here, put in a little code here, and it really feels like that when you get a handle on it. All right, so you process the children's color here, changing the Boolean variables appropriately. Based on what the Boolean variables are, you decide the color here, and you return it. All these colors start returning back. So let's go through it. This one goes here. This one, say, goes here. This one finds a whole bunch of whites. They return white. So this one now is a white. All its children returned white, and it's all done. And it backs up here. So this one now has seen a white in this direction. It goes in this direction. It sees an empty. Keeps going in this direction, sees another white. Finally comes back here. It returns white because it's only seen whites. This one has only had one child, and it's seen whites. So this one returns a white. And now this one's done. We're finished. We're back in this section. When you come out, you count how many nodes were in that component, how many E's were there. The color of all of them is the color of the depth first search that just finished. It's the return of that depth first search. If this one returns white, then all of these are white. And whatever that number is, you don't even have to keep track of what the nodes are. You just have to keep track of how many of them there were. You add that number to a counter. And then you keep going on in your loop, and you start again. You get a whole bunch of new E's that will be connected. The last depth first search of those E's returns a black, a white, or a gray, and you update the counter appropriately. That's a sketch of how to do that problem. Don't do it from scratch. It is okay if you feel like you still have no idea how to do it. If you haven't worked on it yet, you might still feel that way. But have the comfort that if you find me and I sit down with you for 40 minutes, I can write this code with you and you'll get it. And if you think about it for a little more, you might feel a lot less lost than just this minute. Yeah, 1 second, John. You need black, you need white, and you need gray. You can't just return black and white because otherwise, when you get a mix, you have nothing to return. You have to decide on the color to return here, and the values can be black, white, or gray. Absolutely. Good point. I'm glad you clarified that. Yes, Doug. 1 second.
Some of them we're going to need to look at them 2 times. For example, the W that is part of that large group on the right. It's part of the small group, the W and E below it, and the W and E with the E above it. Yeah, the W is going to be marked the very first time we encounter it. So do we need to reset our account at every single time? We can't use our...
Very good point. In the regular connected component algorithm, you look at every node once. You look at every edge once on each end. But here, the way to decide that you've reached the edge is to find something marked with W or B. So just because you've marked it the first time, you're not going to change its color, and you might actually have to go there again. So you'll go there, and it's marked, and if you don't do a depth first search, you'll never find out what the color is. So you're right. You're going to have to not mark things for the next round through. You're going to have to unmark things that are W and B. That's a subtlety, and it's a peculiarity, but it's true, and it's a good point.
In that big circle,
yes.
you could potentially have one node think that he's white and another node think that he's black, but really they're both gray.
No, wait, in here?
Yeah, because say that E that you...
This one?
You said he thinks he's white because he's gone to...
He thinks he's white so far.
Right, but then he returns white.
He returns white to this one. And then say later on this is black. Let's do that.
Right.
So finally, this one finds out that he's really gray. This is the first one that finds out he's gray. Right? And he returns that gray to the original one that made the call.
Right, and then all of them become
Then all of them are gray.
Right.
It's the last one that finishes, that color is the color of all the ones you've seen in that depth first search.
Right. But as far as that individual one out there, he only knew.
Who gives two hoots,
Yeah.
as long as we keep track of what his color really is. And if you want, you could actually keep the nodes in a stack, and when you're all done with the component, pop them off the stack and recolor them all to the right color. And you would really do that if you were actually playing the game, because you might want to have a data structure that actually has the color of these things in it. Yeah. I'm only asking you to count them. But right, it's a good point. You're right, I'm leaving a lot of garbage as I go, and if I wanted to clean it up, I'd have to clean it up at the end. I don't need to in this particular problem, but I could. Yeah.
Shai, but doing that, we talked yesterday about pouring gray paint down in the cave. We have these analogies.
Right.
It makes a good debugging tool to be able to print out.
It's a super, right.
With little, in my case, little W's, little B's, and little G's to say what the empties.
Right. Todd's method is to have a tentative white, a tentative black, a tentative gray, and then when he finally knows the real colors, he turns them all to capital letters.
Or something like that.
Right.
In any case, when I
More or
unroll
less.
the stack, I actually do recolor.
You actually, right. So you actually keep track of the nodes in a stack, and when you unroll the stack, you recolor these things. That's a clean way to do it. That's the way Jeff would do it. That's the way a careful engineer would do it. And the way someone who's just trying to get through the problem set and wants to make sure that they understand the idea, and they don't care about the next problem that's coming up that might build on this, they wouldn't bother. And then when the next problem comes, oh, I wish I had done that. So go borrow the code from Todd or Jeff, and you're all safe. Okay. Okay. We're doing well. We're doing well because I'm sensing the questions are good. Every question is showing an understanding. Unless you are making an active attempt to fool me, I feel you know what I'm talking about. You're succeeding. There's dozens of ways to use depth first search. I picked a way that I thought was in the middle, not a way that I'd give you a month just to think about what the heck to do with depth first search, like a planar graph. I could give an assignment, write depth first search to decide if a graph is planar. And I'd put 8 months on the time expectancy. I mean, you just can think and think and think and come up with no idea. But the problem I gave you is a problem that you can definitely get, but it is not just a trivial flush in a couple lines. But you will get depth first search, and you'll master it if you can do these variations of it. A really cool use of depth first search, where the reason it works is hidden behind a bunch of interesting theorems, is the one I'm going to do now. The theorems are in the text, and you can look through them, and why it works will seem like magic, and we're going to leave it as magic, but the implementation and the details will be crystal clear. Right? And this is an algorithm that does something called strongly connected components. It's the last one we're going to do. There are many others, like I said. One of the problems is on biconnected components. Sometimes I do that one, because that uses an undirected graph. But this text has a whole chapter on strongly connected, and I decided rather than talk for a long time about a problem that you'd have no reference to, let me talk to one that you have a big reference to and can stare at for 20 pages. So strongly connected components. It is so easy to describe this algorithm. So I'm going to write an example, describe it in 3 lines. We'll run through the example. We'll marvel at the fact that it works, and then move on. I want to see some good marveling. It said oh. Gotta be Bach. Alrighty then. Yes, okay. Here's a graph. What are strongly connected components? Some of you are either completely understand that and want me to go on, and some of you are thinking, I hope to God he reminds me. So I'm going to remind you. A strongly connected component in a directed graph. It's got to be a directed graph. There's no such thing as a strongly connected component in an undirected graph. A strongly connected component in a directed graph is a collection of nodes in the graph, each of which has a path to each of the others. Everyone understand that definition? So, is this whole graph strongly connected, all the nodes together?
No.
Why not, if it's not?
You get stuck.
Because the
because this one can't get to this one. If you can find two nodes, one which cannot reach the other, then those two nodes are not in the same strongly connected component. These three nodes are in the same strongly connected component. These three nodes are. Any other connected components, strongly connected components? There's this guy all by itself. So the strongly connected components in this graph are these three, and that guy. All right?
So in what sense can that bottom guy get to itself?
He just stays there.
Doesn't that mean all the nodes are
Which guy?
are strongly connected with themselves?
Here's one. Here's two. Jesus. And here's three. Every directed graph can be split up into an equivalence class of strongly connected components. These three are considered the same. These three are considered the same. This is considered the same. Three different components. This is useful for the same reason that in an undirected graph you get connected components. In an undirected graph, if you want to find minimum spanning tree, and it's separated into 20 components, well, you just run minimum spanning tree on each component. But you got to be able to find the components first. Here too, there's a lot of algorithms that work for directed graphs, but you'd like to first run them on each strongly connected piece because they only run on strongly connected components. So you'd like to just split the thing up. Another thing is you want to, I don't know, you're in the army and you want to destroy the communications network of the enemy. So you want to identify what are the different units that can all communicate to one another, because that helps you focus on your destruction. Oh, I'm going to knock on the door. They're going to take my Department of Defense grant away. Okay, how do we figure out the strongly connected components?
You're wearing paratrooper pants today.
Yes. That's right. Ugh. Oh, geez. Forgot that wall was hollow. Drop and kick the wall. Okay, here's the algorithm. It's 3 steps. Do depth first search and calculate finishing times of each node. When was finishing times useful? What other algorithm? For topological sort. The finishing times of a depth first search gave us in reverse the topological sort. It was useful there, and it turns out to be useful here, but for an unrelated reason. Calculate the finishing times for each node. Step 2. Reverse the edges in the graph. Step 3, yeah, I know. Call depth first search on the nodes in the reverse graph in reverse order of the finishing times. Woohoo, yeah. This is like the reverse algorithm. Let's do it. If we do it, you'll understand what this means. It's not that tricky, but it's very high level, because I'm just saying do a depth first search, do another depth first search, reverse the edges in between. So let's do the first depth first search together. Let's keep track of the finishing time. All right, so we start here. Let me label it with A, B's, and C's. A, B, C, D, E, F, G.
And you can start anywhere.
Yeah, I always assume that the data structure is in alphabetical order for purposes of examples, so that in your array, the first node that shows up is always A. But you could start anywhere. All right, we start at A. Where do we go next? Then G, then D. And now we're done. We're going to back up. So I'm going to mark these, right? This is 1. That's the first one to finish. 2, second one to finish. 3, third one to finish. I'm going down here to F. So this is the fourth one to finish. Back to here. Oh, I left. Huh? Yeah, it's right, except nothing.
Why did we go to F?
Oh, because I backed up to B and then I had to go forward again.
Yeah, but you would go to.
Wouldn't you actually go to?
Oh, I'd go to E. Yeah, I would go to E. Forget that. Oh, I was wondering why my thing looked funny. I'd go to E, right. This would be the fourth one to finish. Come back to B, go to F. This would be the fifth one to finish. Good. Now it looks right on my notes. 6, and now finally 7. Those are the finishing times. Where do you calculate finishing times in your skeleton? Come on.
The end.
Here, where it says decide the color, the end, right. There's a way to fool me that you know what's going on. Depth first search I. There's 3 places. Before you do the search, in the middle of the loop, after the search is over. After the search is over, you mark the finishing time, you increment your number by 1. Right there where it says decide the color in that other algorithm. So there's the finishing times. Next step, we're going to reverse all the edges. What's the best way to do this? Rewrite it?
Different colored chalk.
Different color chalk? Did you throw your voice to say that? Let's take a vote. I know you didn't mean it. It was a joke. I know. But we're doing it anyway. It's so easy to reverse edges. Tell me if I make a mistake. Oh, it is easy algorithmically. Oh, it is.
Ooh, and we marvel.
Is that it?
Isn't there a cost?
Just make sure I reverse them all right. And now that Chris has brought up that question, okay, it's there. How do you reverse the edges in a graph?
You have to go through J.
You have to go through that whole adjacency list and say A connects to B and C, right? What does that tell you? That means B's got to connect to A and C's got to connect to A. So you go to create your new structure. In the array slot for B, you add an A. And in the array slot for C, you add an A. So how long does it take to do this? You run through your first structure once, and you copy along, make your new structure. It's not so bad. It's order E.
Are we going to write this?
No. What if I had it in a 2-dimensional array? What if I had it in a 2-dimensional array instead of adjacency lists?
Transpose?
Transpose. Okay, everything that used to be in location ij is now in location ji. Okay, so if you ever wondered why the heck you learned what the transpose was back in month 0, it's just so I could use the word now. All right, the transpose of the array. And that takes n squared. Right, you got to go through every pair ij. So we can do that in relatively fast time compared to the rest of our depth first search. This takes order E. This takes order E. And now the last stage is going to take order E. So 3 E's. That's pretty darn fast. So we're up to step 3. Call depth first search on the nodes in the reverse graph in the reversed order of the finishing times. So we are going to use the finishing times to imagine that that's the order in which we should depth first search the graph. That means this is like A and this is like B. Everyone understand? That means you just recopy the graph in order so that your new array is the same index as these finishing times. So we start here at vertex 1, and we're going to do a depth first search on the reverse graph in that order. So let's go do it and see what we get.
You said in reverse order of the finishing time?
No, I mean reverse order.
So we're starting at 7 or
Starting at 7. Yeah, sorry. Yes. Thank you, Michael. You asked that very politely. I wrote it one way and I said it the other way, but I meant what I wrote. You start on the reverse graph, as you know. Let's start here and go in reverse order. So we start here, and let's keep track of the depth first search tree as we go. Here we go. What's next? What's next? So I back out, and I go back into my nested for loop, right? Because I'm backed at it. Remember, I wrap everything in there. So I go to the next spot, which is F. See the importance of the orders? Because it relates to which one you start on next. Go from here, and you get...
Why don't we start at 6?
6 is done.
6 is finished.
Oh.
It's marked already. So we start at 5, and there's no place to go. So there's no edge here. The parent of this is here, and the parent of this is here, and the parent of this is nil. So I'll just box that out so we know it's marked. Then we go to C, and we go forward and marked. Here's the result. In this depth-first search, every connected tree represents a strongly connected ponent in the original graph. See this tree? These 3 nodes. This little weenie tree with no edges, single node, and this little 2-edge tree, the other 3 nodes. So when you're all done, this keeps track of the depth-first search tree in a parent array. The parent array, when you start to run through it, is going to have connected parts and disconnected parts. You run through one, you go through all the parents, and anytime you get a disconnected one, you say new strongly connected component, and you print that out. All right, this is a cool algorithm. It's neat. It is interesting to think about why it works, and it would help you come up with your own algorithms for similar things. But we don't have the time, and I wanted to just show you it as a neat example that is easy to understand and how you can build depth-first search algorithms into really very powerful things. All right. Questions?
This one's in the book.
You bet.
And it tells us why it works.
25 pages worth. Lots of theorems. It's hard to prove that these things work. It's tedious. It's a long process. Anytime you write a paper on this stuff, most of it is explaining why it works, and the last section is a little intuition and some details about what I talked about. So it's tricky. I once refereed a paper on exactly this topic, which was explaining how to solve it with a parallel algorithm, which was really hairy. It took me weeks to referee that paper and understand what they were talking about. So as hard as this is, it can get worse. All right, I'm not done yet. I'm not done yet. I'm not done yet. Take a deep breath. I'm still not done. I'm done with the depth-first search. I'm done with breadth-first search. But I want to introduce the next topic and spend some time on it, and then I'll let you go. Back to Todd's bike wheel.
Looking better.
All right, here's an undirected graph with some edges on it. We're going to talk about a problem called the shortest path problem. I want to get moving on this for a little while, just so we're into the very last topic of graph algorithms, and I can finish it up on Monday and move along. Shortest path algorithms are not going to be so bad to understand. They're easier than what we've just done. So if your head is a little bit cloudy, just take a deep breath, and this will be a little better. A little intro to shortest path problems. They're very practical for obvious reasons. You want to be able to find the shortest distance from one place to another, the smallest cost of what it might be to pipe, energy from this point to this point. It's something that comes up all the time. There's a lot of different versions of shortest path problems. There's undirected graphs, undirected graphs. There are versions where you have all positive edges. This kind of problem can be solved in either n squared or e log n. And the two different algorithms are similar to what we did last time with Prim's algorithm. This one uses a two-dimensional array. This one uses adjacency lists with a heap. Okay? And these are sometimes due to a guy named Dijkstra. There are other people who came up with these ideas, but it's sometimes called Dijkstra's algorithm. There are algorithms for shortest path that run on directed acyclic graphs. That means that you have directed edges, but there's no cycles. The algorithm for this is kind of folklorish. I don't think anybody knows who came up with it first. But it can be done in order E time, very fast. Even if there's negative edges, with negative weight edges. As long as there's no cycles, speeds you up. Okay, questions? Next step. Let's add negative edges and put cycles back in. The only thing we can't have, so I'll write general graphs, means negative edges and cycles. But what we're not allowing is a cycle that has a weight that's negative. If you're asking for a shortest path from here to here, and you can find a cycle whose weight is negative, any good algorithm you come up with is going to do this, is going to say, I can give you an infinitely short path, because I'll just go round and round that free cycle. Okay, if it costs me 1 unit of energy to pump here, and this is -3, it goes down a waterfall, I get 3 units of energy, and this is -2, and that's 1, I'm just going to pump my energy this way and take this waterfall and make a lot of money because I get free energy. Right? So negative weight cycles don't usually come up in the problems that you're modeling. But if they do come up, then the problem isn't even well defined. It doesn't mean anything to have a shortest path if you can have an infinite shortest path. If I change the problem to mean what's the shortest path between here and here, but the negative cycles can't be used, if you stipulate that, then the problem is NP complete. That's a hard problem. If I throw negative cycles in the graph and I say, show me the best way of getting from here to here, but don't use that negative cycle to help you get an infinitely better one, avoid it, that's a hard problem.
What if you can use it one time, exactly one time, the negative cycle? Is it still NP complete?
Yes.
So the same would also be NP complete if there were no negative cycles in the graph. There were cycles and there were negative numbers, but there were no negative cycles.
If there's negative edges and cycles but no negative weight cycles, then it's polynomial time. I haven't talked about that yet. That's this general case. And it's order n times e. Slower, much slower, but you can do it.
Should I just say, what does DAG stand for?
Directed acyclic graph.
So having negative cycles and not being able to use them is appreciably different from having no negative cycles?
Yes. A big difference. Here's the difference. Here's the difference, Chris. The presence of negative cycles is going to make any good algorithm go into an infinite loop. And if you don't have negative cycles, then you can have an algorithm that works correctly that doesn't go into an infinite loop. So if you make an algorithm avoid that infinite loop, it loses all its control of what it's trying to do, and the best it can do is try every possibility. That's intuitively what's going on.
Why doesn't,
Yeah?
sorry, why doesn't it just test for negativity on an edge and cancel that?
Well, it might be good to use a negative edge.
It would
But
have to
negative
complete it
cycles.
this
It just can't use a negative cycle.
Oh, I get it.
So I'm going to write negative weight cycles NP complete.
Essentially, it would have to look ahead to find out if it was entering into a negative cycle and eliminate that.
Yeah, but I mean,
Or if the negative cycle happened to be 50 steps long.
it's not just that. It's that the algorithm would do the negative cycle. It would think it's doing really well, and then do the last one, and then you'd say, oh, sorry, you can't do this. And then what's the algorithm supposed to do? It doesn't know if everything it's done up till that point is worthwhile or not. It just messes up the whole correctness of the algorithm. The algorithm doesn't work correctly in the presence of negative cycles.
Damn it, I started on a negative cycle.
What's the relationship between shortest path problem and longest path problem? If I took all these edges and made them negative, and then ran the longest path problem on this, wouldn't that be the same as running the shortest path problem on the positive edges? Right? The biggest negative would end up being the smallest positive. They'd be the same thing. That's called a reduction. I'm changing one problem into another. You want to solve the shortest path problem and you've got a way of solving longest path problems? take my shortest path problem, change all the edges to their negative ones, and run your longest path problem on it. You'll get the right answer. Change one problem into another. That's fine. It turns out, though, that the longest path problem, just like the shortest path problem, is going to be hard in the presence of what kind of cycles? In the presence of positive cycles. So normal graphs that have positive cycles, the longest path problem is NP complete. So because of this, the shortest path problem has a reputation of being polynomial time, and the longest path problem has the reputation of being NP complete. But if all graphs had negative edges, then the shortest path problem would be the one with a reputation for being NP complete, and the longest path problem would be the one with a reputation for polynomial time. Okay, don't think that max and min is what makes the difference here. It's the relationship between what the edges are and what you're trying to do. All right, questions about that so far?
What was the distinction again for positive edges between the two that you have?
This one uses the two-dimensional representation of a graph, the two-dimensional array, and this one uses the adjacency lists, and it has a heap to help, which is similar to the two ways we talked about for Prim's algorithm for minimum spanning tree. We'll get to those details later. Okay. This is intro. I mean, you're not supposed to know how these things work yet or what's going on. Questions?
Is there a consequence for zero weight cycles?
No, not at all. You can have zero weight cycles. Other questions? So what kind of answer do we hope to get back from a shortest path algorithm? Say we want to know the shortest path from A to F. We'd like to have, given A and F, a number that tells us the shortest path. We might also like to actually know what the path is. There's always two parts to this. It turns out that computing one is no harder than computing the other. As long as we're going to compute the shortest distances, we can also compute the paths themselves. Won't be hard to do. We have to decide what kind of data structure is going to send the answer back. And that's also not going to be too hard, and I'll show it to you. But there is one thing that isn't obvious that I do need to explain. If you want to know the shortest path from A to F, it turns out that nobody knows any better way to do it than on the way to find the shortest path from A to all the others. Everyone understand that? If you want to know the shortest path from A to F, then the best way I know how to do it also figures out the shortest path from A to everybody else. So you might as well, when you think about shortest path, think about this kind of problem. Single source shortest path. I want to know the shortest path from a fixed node to everything else in the graph. That takes just as long as a single one. Right? Nobody's been able to improve it anymore. So what kind of thing should come back? What should come back is something called a shortest path tree. And distances. The shortest distances. Let's try to do an example by hand here and figure out what it should come back. Here's the distance array. Distances. And here's the shortest path tree represented by parent. Again, a nice easy structure for a tree, just the parent array. Two arrays are going to come back out of this algorithm. The distance array, the parent array. And we're going to root this on A. We're looking forward from A here. So what's the shortest distance from A to itself?
0.
0. And what's the parent of A? Nil. What about B? What's the shortest path from A to B? You're just doing this in your head now, right? We're just looking for the answer. We're not worrying about how we get it. Shortest path to B is 2, and the parent is A. Yes?
If, say, the distance between A and C was 1 and C and B was 2, but the distance between A and B is 4, I know, but how do we find that?
Well, we're not doing the algorithm. We're just eyeballing it.
Okay.
You know how we'd find it? We wouldn't have marked B. We would have marked C first.
Okay.
If you always go to the shortest one first, then you never have that problem. But you're looking ahead. So you have to shut your brain down for a minute. Just What's the shortest path from A to C? It's 1, and the parent is A. The shortest path from A to D is 1, and the parent is A. The shortest path from A to E. Okay, we're doing this in our heads, right? This isn't the algorithm. This is just us eyeballing it. And the parent of E is, right? Because the path goes this way. And the shortest path to F is 3. And the parent is B. So that's what it really looks like in the computer. And if you want to make a picture of it, it looks like this. With the appropriate distances stored at the nodes. Every shortest path algorithm, that single source, will return a shortest path tree that looks like this, with a parent array and a distance array to tell you the distances. Now you can recover the paths by running through pointers backwards, and you can recover the distances by just looking them up. Questions? All right, last thing, 10 more minutes, and we're done. 10 more minutes. Let's go back, erase all this. We're going to do it all again now, and we're going to talk about this variation. Leave these for another day. Let's really do it the right way, instead of just eyeballing it. This variation is due to Dijkstra. It's a very well-known algorithm. And here's the idea. We initialize the distance of A to 0. Okay? And we set its parent to nil. That's because we're starting at A. That's the beginning. Now we're going to go into a big loop. And what this loop tries to do is scan forward from each node in some order. And when it scans forward, it updates parents and distances. Now what I mean by this scanning is something very specific, and it's very logical. And the whole trick to a shortest path algorithm is what order you're going to do the scanning. If you understand what the scanning step is, all you have to do is figure out what order to do the scanning, and every one of these falls into the same paradigm. So what does scanning mean? Let's get rid of the shortest path tree. 1, 1, 2, 1. Scanning a node means looking forward down the edges and asking yourself, is the current best distance to B, C, and D better than the current distance to A plus this edge? In other words, if I use this edge, can I get to C better than the best way I know up till now? What's the best way to get to C right now? What should all these distances be initialized to? No, not 1, because they're too small. It's got to be something really big, something that's going to get replaced, that's going to get smaller. Right now, think of, as far as what we've seen, all the nodes being disconnected from A. We haven't looked at any edge. So these start with really big numbers. And the first thing we do is we look forward to A, and we look at all the different edges, and we label them, if necessary, by the better distance that we just found. The best we can do from B, C, and D right now is infinite. But now that we've looked at here, we know we can get to A in 0. Plus 2 gets us to B in 2. So I can get to B in 2, and the parent is A. I can get to C in 1, and the parent is A. And I can get to D in 1, and the parent is A. So I want to make a little change according to what Chris asked, so we'll see what's going to happen. Let's make this 3, if nobody minds. 4? Okay. And leave everything else the same. So as far as I know now, the best way for me to get to B is 4, and it's through A. The best way for me to get to C is 1. The best way for me to get to D is 1. A is now scanned. We will never look at A again. It is done. Exit out. Finished. The question is, what do we scan next? All we're going to do is scan now. Scan, scan, scan until you're done scanning every node. And the key thing is we're going to scan every node exactly once. We never have to scan a node again if, Donna, if what? What do we do next?
one where a short path comes?
Right. Look at this list of distances and pick a node that has the shortest one of all of them. If you scan from the shortest current distance first, you never end up scanning a node more than once. You never have to. That's a key thing. In other words, A's distance will never change. Once you scan a node, its distance never changes, so you have no reason to ever go back and scan it again. If the distance to a node would change, you'd have to go scan it again. So if you scan in shortest current distance order first, you never relabel that node later on. And there's a theorem that says exactly that. It's kind of intuitive. I mean, Donna just guessed it, and she's not as famous as Dijkstra, so there you go.
Yes. Smart. That's what you're going to say.
No. What I was going to say is Dijkstra can't dance as well as you. All right, let's go on. Good recovery, yeah. Let's scan forward. It doesn't matter. C or D is equally. OK, so let's scan forward from C, and I'll cross this out. Let's scan forward. C goes to 1. Right now, we can get to C in 1, add this extra edge 2. We can get to A in 2. But A is already gone. We have to talk about the implementation later. Tzvi's right. A is already off the list, and we actually wouldn't look at A. So let's go this way. C goes up to B. The current value of C is 1. The edge to B is 2. So now our B gets to be 3. And its parent gets to be C. That's a change. And that's why we're guaranteed to find it, because we're going the shortest first. We'll never lose that. C goes to F now, right? Let's finish it up.
F is 5.
So F becomes 5. C is 1, and 4 more makes 5. And the parent of F is C. And C goes to E, right? And that becomes 4. And this becomes C. And then C goes to D. That makes 1 plus 4 is 5. But B was already 1. So we don't change that. So now C is scanned. C is gone. We go now to scan from D. D is our next smallest. Scan from D. We go forward to E, and we get 3. So E is now changed, and this parent goes to D. Now we scan. We're done scanning D now, right? Now we scan, what's the next? We're done with C, we're done with D, we're done with A. So between B, E, and F, I guess we scan B. BF gives you 4. The current best for F is 5. Right? B's current value is 3. Add this extra edge is 1. So now we can get to F through B. And this goes down to 4. And this parent goes to B.
So now you sort of created an ambiguity, haven't you? I mean, in terms of your list here, you don't really know your path back to A, except... Sure you do.
Yeah. If I want to go, F is going to go back to B, and B is going to go back to C, and C is going to go back to A.
Okay, I'm done.
No, you're not done, but I just want to make sure that it's right.
You're just not famous as Dax.
And he can't dance as good as Donna. Now I lost where I was up to. We just scanned through B. Did we finish scanning B? I think we did. Now we're going to scan through E. E is 3. It has an edge to F. That's 1. That makes 4. That's the same as what we have. Depending on how you implement that algorithm, you'd either change it or not. Usually you don't change it if it's the same. So you leave it. That means E is scanned. And now F is scanned. There's nothing to scan it with, so you check it. And these are the best distances, 0, 3, 1, 1, 3, 4. And this is the parent pointers. This is Dijkstra's algorithm. All right. Now I have just 1 minute left to analyze it. 1 minute left to analyze it. How do we do it? You have 2 arrays. You got to be able to pick the smallest out of this distance array at any time. You got to be able to do this scanning forward. You scan every node exactly once, right? We guarantee it. Never have to scan a node again. What does the whole collection of those scannings cost? N squared if we have a 2-dimensional array. and E if we have the adjacency lists. You hit each edge exactly once. And you do one if statement on it, comparing the current distance plus the weight to the current distance on your destination. Okay, that's order E time. Or order n squared, depending on how you implemented your data structure. If you did it with n squared, then every time through, every iteration, you could go ahead and scan for the minimum. It would take you order n time in each of the n iterations. Every time you scan a new one, you want to figure out which one to scan, take linear time and figure out which is the minimum. So that doesn't increase the complexity, because in every step, you're doing a constant amount plus a linear amount, and you have n steps. So it gives you n squared. And there's an easy implementation, no big deal. Calculate a minimum, do a constant work, scan the next one. But what if you wanted to have it with the adjacency lists? With the adjacency lists, you're not looking through the whole n nodes in each step. So you don't have linear time in each iteration to look. How are you going to find the smallest one to scan next? You all want to go, but you have to answer this question, and then you can go. How do you find the one to scan next? Use a heap, or a red-black tree, or anything that does a priority queue. You chuck all your nodes into a priority queue, whether it's a heap or a red-black tree. Something that lets you find smallest things in constant time and fixes itself in log n. How many times do you have to use that heap? One time for each node that gets pulled off, that's n. But every single time you look at an edge, you might have to change one of these values. And when you change a value, you have to fix the heap. So that means you can manage this, but for every one of the E steps that we used to have, and for every one of the N steps that we have for pulling the nodes on, we have log n work. So n plus E times log n, which is the same as E times log n. That's where the E log n comes from, heaps with adjacency structures like Prim's algorithm, and the n squared, it's a little more, but you get the minimum calculation for free because you have n iterations of n. All right, so everything, I did a lot today. I squeezed this last part in the last 2 minutes because it's similar to Prim's, and I wrote details on it in the notes so you can look at it, and it isn't too bad. It's not so complicated. But I'm going to start next time right here on these two variations. And they are the same thing except a different order for scanning. All right? This one never does anything more than once. This one has to scan something more than once. And that's why the analysis is complicated.